All right, let's get started. As some of you are gleaning from the AutoCAD file, I thought we would play some football today. But that'll become clear as to why we did that here in a bit. All right, let's get started. Welcome to Lecture 16. We are in week 9. I can't believe it. So we have one more week before spring break, and then only 4 more weeks after spring break, and we are done. So we are definitely on the second half of this semester. Just a quick heads up on logistics. So the attendance grades are up to date. All the homework grading is up to date. Obviously, other than the one that's due today. And again, my apologies on the typo, the typos and whatnot on the layer assignments on problem 1. But 73 of you have submitted. A few of you are still remaining. Are there any questions remaining on homework 8? Everybody good? Okay, just remember it's due by 5 p.m. today, and we're only submitting the PDFs for this one. Okay, no drawing files, just the PDFs. So there should be 2 files submitted for homework 8, one for each of the drawings. So how many files are we submitting? 2. How many? 2. All right. Okay. I don't have a homework assignment for you today because I have one on Wednesday. And I'll tell you that the one Wednesday, I don't want to say it's our biggest assignment, but it's one of the bigger AutoCAD assignments because it's going to require you to use your scales and your 3D brain, as it were, to generate a drawing. Okay. Any other questions? Everybody good so far? Okay. For you Mac folks, and really for anybody who's not a Mac user, I wanted to mention something called Cameo because the university just went live with Cameo like on Friday. So just so you're aware, Cameo is a platform where it stores a lot of the university applications and whatnot in a cloud-based setting. So anybody with Marshall credentials has access to Cameo. Okay, and the website is just cameo.marshall.edu. The way it works is that you log in with your Marshall credentials, okay? And when you log in, the main page looks something like this. And what it contains are all of the apps and programs that you as a Marshall student has license for. And one of those is Inventor and one of those is AutoCAD. So for example, if you open up Inventor, you actually get sort of the Windows experience with Inventor. Okay, they just went live with this like on Friday. Okay, so the point is, when we come back for spring break, we're using Inventor, and unfortunately, Inventor is not Apple friendly. But if you'd like, you can use Inventor through Cameo, and it's pretty much the same experience as you get on Windows. So I just wanted to throw that out there. But also for you folks that are Windows users, AutoCAD is available here as well in case you're having some licensing issues or whatnot. It can be a little bit on the slow side because it does depend on your Wi-Fi signal, but if you've got a strong Wi-Fi signal, it works just fine. It's a really nifty little platform. I just started messing with it this weekend, and it's really cool. So I did want to mention that in case anybody wants to use it. So again, it's just cameo.marshall.edu. You log in. Sound good? Okay. Any questions? Okay. All right. So I know it's been a while since I mentioned this, but I had everybody buy one of these, right? Everybody get one, bring one. If you did not bring it today, it's not the end of the world, but you do need to bring it on Wednesday, okay? And just to make sure that we're clear, does everybody have an engineer scale, not an architect scale? Engineer scale? Okay, all right. So I want to talk about engineering scales and what they're used for and how and what their purpose is. Okay, and the use of this tool can greatly expand your ability to produce engineering drawings. And some of you are thinking, well, it's just a ruler. Yeah, but there's a little bit more to it than that. And there's a method behind its design, why it's structured the way it is, why there are 6 scales and not 9. There's a lot going in here. So I kind of want to talk about this a little bit, but specifically I kind of want to make the point of why we even need one of these. Okay, and the best way to explain that is with this. Okay, let's say that I wanted to produce a scale accurate drawing of the Eiffel Tower. it's kind of tough to print that on an 8.5 by 11 sheet of paper given how tall the Eiffel Tower is. I've been on top of the Eiffel Tower. That thing is huge. You know, there's no way that's fitting on a piece of paper I can fit in my backpack. Okay. So the only way to produce an accurate drawing is to scale it, to produce that drawing to some scale. Okay. Honestly, up until now, a lot of the parts and the components that we've been drawing and fabricating, they have been structured in such a way that all the dimensions are 1-to-1, and they can fit on an 8.5 by 11 or an 11 by 17 or what have you. But the honest reality is rarely are we as engineers producing drawings to true scale. We are rarely producing components where 1 inch on the drawing is equivalent to 1 inch on the actual object or 1 unit on the actual object. A lot of times what we're doing is we're drawing elements that are much larger than what could fit on the sheet of paper or much smaller, okay? It's possible that you are trying to produce engineering schematics for an object that's like this big, and so but you need to blow it up so that the part and its configuration and its geometry are very clear. So a lot of times what will happen is 1 inch on the paper will equal so many units in the real world. Maybe it's so many feet, maybe it's so many millimeters, maybe it's so many yards or what have you, okay? And the best way of measuring dimensions on a drawing like that is with one of these, with an engineering scale, okay? Now, just to give you kind of an idea of probably the most ubiquitous use of a scale, it's to interpret existing drawings. Okay, so let me just paint a scenario for you. Okay, let's say that you're a civil engineer and you're working on a roadway improvement project. Okay, so you see this old road and this newer road which is going to be installed. And so there's a guy out there who's got some land. He's getting ready to build a house, and he says, "How far is that house going to be, or how far is the new road going to be for my house?" Now, you have engineering drawings. You didn't dimension that. You didn't do that, right? You didn't dimension that. You had no idea that a house was going there. But you have a question that needs answering, okay? How do you answer that? Well, the answer is with the scale, okay? So, for example, this drawing has been printed such that 1 inch on the page equals 20 feet in the real world, right? So if the homeowner says my house is going to be about right there, break out an engineering scale, measure it, and you can determine the distance, okay? The idea is that it's sometimes not feasible to dimension literally everything on the drawing, okay? But I propose that if you print a drawing to a known scale, then in one way, everything is dimensioned. Like if you know the scale of the given plot, then with this, you can determine any dimension on the drawing, okay? And I would argue that printing to a known scale is a means of annotating dimension. I told you that there were really two ways of dimensioning a drawing. There's the direct approach, which is actually listing the dimensions, and then the indirect approach, which is printing to a known scale. That's what we're talking about here. Now, an obvious question about this thing is, well, Dr. Mike, can't we just use a ruler? Like, couldn't we just use a ruler to answer this question? Like, why do we need this fancy thing? Okay? Well, I want to explain why. Okay? So, so first off, okay, does anybody notice anything different about the way that this is configured? I tell you what, if you've got your engineering scale in front of you, I'd like you to turn to the side that has the number 10 on it. Okay? All right, does everybody see the side that has 10 on it? Okay, does anybody notice something different between how the tick marks are lined out here versus how they're lined out here? Anybody notice how they're a little different? How many tick marks are per inch on the 10 scale? 10, okay? That's different than a ruler, okay? A ruler, so I have here an image of a ruler that you probably had when you were in grade school or high school or something like that. And if you look at the gradations on a ruler, the gradations are in like 1/16 of an inch. So it's like half, a fourth, an eighth, a 16th, so on and so forth. An engineering scale is different. An engineering scale is in tenths or 20ths or so on and so forth. Because a ruler is in 1/16 of an inch, it can complicate scaling distances. Okay, so to kind of make the point, just on the geometry. So a ruler only has one set of graduations, typically to a 16th of an inch, usually not more, okay? Whereas an engineer scale has 6 sides, okay? And each of those sides list graduations that are essentially in tenths. So for example, the 20 scale, so if you look at the 20 scale, it says 0, 1, 2, 3, 4. In between each of those numbers, there are 10 tick marks per graduation, okay? Now there's a 10, 20, 30, 40, 50, and 60, but there isn't anything beyond that. And the main reason why is if you look at the 60 scale, which is the finest one, those tick marks are getting pretty close together. I mean, at that point, do you think you could actually read a scale that's like 70 or 80 or 90? Probably not, you know, so 60 is probably pushing, okay? That's about as far as you could go, because past 70 and 80 and 90, they'd be kind of tough to read. So why don't we have a 70 or 80 or 90? Well, just look at the 60, and that's the reason why. We really couldn't read them very accurately if we wanted to. Now, let me sort of make the point as to how an engineer scale makes your life a lot easier, okay? So I want everybody to look up here on the screen. So I have here an object. This object is in green, and I want to know the length of this object in the real world, okay? Now let's say that this object is printed on a drawing such that 1 inch equals 50 feet, okay? So what do I do with a ruler? Okay, I go to a ruler and I measure the length, okay? Now I'm looking here at this screen and I'm thinking that length is about 4 7/8 inches. I mean, everybody kind of agree with me on that? Sure. Yeah. So in order to determine its length in the real world, I got to break out my calculator because I say, okay, 1 inch equals 50 feet, and the drawing is 4 7/8 inches. So 4 7/8 times 50 is about 244 feet. Okay, so I have to use a ruler in combination with some calculator. Okay. Now, what if I ask the same question with an engineering scale, and I said, what's the length of the object if the drawing is printed at 1 inch equals 50 feet? The beauty of an engineering scale is that when it comes to the actual length of the object, I don't really care, okay? Because all I have to do is turn my scale to the 50 scale. Let's zoom in right there, zoom in a little bit, and we can kind of see how it's about, you know, we got 22, 23, 24, 24 and change. What is that, 24, 1, 2, 3, 4, maybe about 244 feet? I just read it, okay? So the beauty of an engineering scale is that you don't have to do any math. You don't have to take the measurement and then compute some length or compute some distance. Because you know that the drawing is printed such that 1 inch equals 50 feet, the idea is that on the 50 scale, every one of these tick marks is 1 foot, okay? So just measure, and however many tick marks you get, that's the dimension, okay? Does that make sense? So it makes your life a lot easier for determining scale with one of these, okay? So that's really sort of the value of why we use an engineering scale over a ruler, is that it eliminates the need to do any math for a scale conversion in order to determine a distance, okay? So here's the thing about engineering drawings. Whenever we produce engineering drawings, we produce them in these sort of multiples. So for example, let's just, for the sake of discussion, let's do inches and feet. So we can produce drawings such that 1 inch is 10 feet, 1 inch is 20, 30, 40, 50, 60 feet. We never use like 1 inch equals 70 feet or 1 inch equals 90 feet because we couldn't use a scale with that, okay? So if we get to a point where 1 inch equals 60 feet isn't gonna work, instead of doing 70 and 80 and 90, we'll just bump it up to 100, okay? So we can produce 1 inch is 10, 1 inch is 20, 30, 40, 50, 60. Then we might do 1 inch equals 100 feet. 1 inch equals 200 feet. 1 inch equals 1,000 feet. 1 inch equals 6,000 feet, what have you. Any of these multiples of 10, 20, 30, 40, 50, or 60 will work, okay? Does that make sense why we wouldn't use anything different? Because again, we can't use this directly, okay? Now, whenever we produce an engineering drawing, we will that is to scale, we will typically place a scale block on that drawing, okay? And I sort of held off on handing these out because I'm going to show you this later. But I have here a drawing of a football field, okay? And if you look at the bottom, I have a little scale block, Okay. Now, a question might be, is there a reason, like why would I include this little scale block right here if I put here in the title block that 1 inch equals 40 feet? What is the purpose of the scale block if I told the user that 1 inch equals 40 feet? Well, a good reason is to check the scale of the drawing. For example, if I turn to my 40 scale, let's see, where's my 40 scale right here, and I place my 40 scale on this block, you'll see that it's exactly 40 feet. So it's a way of verifying that the scale of the drawing is indeed correct. Okay? Does that make sense? Don't worry, I'm going to hand these out here in a little bit. Okay. Now, whenever you read an engineer scale, the idea is you place one end of the line at the 0 mark, and you place the other end of the, so you place one end of the scale such that the 0 mark is on one end of the line, and on the other end of the line, you just read. Now, typically what you'll do is you'll count the number of tick marks, and then you'll do an additional digit that is estimated. So, for example, like on the 10 scale, like if you had a line that was, about yay long, you may say that line is 34.4 feet, okay? Because the idea is that you can estimate one more amount of precision between the ticks. Now, you'll typically do that on the 10 scale, the 20 scale, and the 30 scale, but on some of the finer scales, that gets kind of tough. It's kind of hard to estimate one dimension past that on the 40, 50, and 60 scale. And don't worry, that is that's going to make sense here in a little bit, because we're going to do a quick example on that. Now, the idea is that if you ever have a drawing that's printed to a multiple scale, like 1 inch equals 100 feet, 1 inch equals 500 feet, just take the number of tick marks, multiply it by 10. If it's on 1,000 scale, take the number of tick marks, multiply it by 100. And again, don't worry, we're going to have a quick practice on this here in a second. Okay. Is everybody with me so far on the ideas? Okay, this is where you as the engineer have a little bit of agency over what you're going to do here. So I kind of want to take some time on this. Okay, so you as the drafter, you as the engineer are going to be the one responsible for choosing the scale of a given drawing. So if you're drafting some plans for a bridge or a roof vault or what have you, you need to choose the scale that you print those drawings at. Okay, and typically what we want to do is maximize the usage of the page. Okay, we want to make sure that the page is being used as much as possible. In other words, if I'm going to have a drawing that's on a 24 feet by 36, 24 inch by 36 inch sheet of paper, I don't want a detail that's that big. Okay, in other words, if I'm going to print, I want the drawing or the schematic to fill up the sheet as much as possible. Now, to give you kind of an idea of how we would do this, okay, I want to introduce just some maximum real-world distances. So let me ask you a question, okay? Everybody follow with me on this. So if I had a base scale on a drawing such that 1 inch equals 10 feet, what is the largest real-world distance that I could measure with one of these things if 1 inch equals 10 feet? What's the longest distance? Say it again. 120 feet. That's exactly right, okay? Because this has 12 inches, okay? This has 12 inches. 12 inches, if 1 inch equals 10 feet, the maximum distance I can measure with one of these things is 120 feet. Everybody with me on that? So for 1 inch equals 20 feet, it would be, what would it be for 1 inch equals 20 feet? 240, okay? Everybody kind of getting the idea? 240, 360, 480, 600, 720, so on and so forth. What if 1 inch equals 100 feet? What's the longest distance I can measure? Say it again? 1,200 feet. That's exactly right. So you're all kind of getting the pattern, kind of getting this idea? Okay. So I want you to sort of keep this thought process in your head, because right now I want to give you an example of how this would work. Okay? And let's say that you were responsible for producing a drawing of a football field. Okay? So that's probably kind of making the idea behind the engineer or the drawing file that I uploaded. That's probably starting to have that make more sense. Okay? So let's consider a football field. Okay? So a football field is 360 feet long. Okay? It's 360 feet because it's 100 yards and two 10-yard end zones, right? That's 120 yards, 3 feet a yard, that's 360 feet, right? So it's 360 feet wide and it's 160 feet tall. With me so far? Yeah. Okay, so what I want to do is try and figure out what scale should I print this drawing to such that I'm maximizing the use of the page, but that the football field actually fits on the sheet of paper. And we're going to use an 11 by 8.5 as our standards. I want to print this on a sheet like this, okay? But I want to print the scale. Sorry. All right. So if we're talking about our distances, our target dimension for the sheet is going to be the size of the football field. Okay, 360 feet by 160 feet. Everybody with me so far? Okay. So let's say that I used a scale of 1 inch equals 10 feet. Okay, if I use 1 inch equals 10 feet, I propose that the biggest object that I could put on an 11 by 8.5 sheet of paper is an object that's 110 foot wide and 85 foot tall. And that's if the sheet or the object encompassed the entirety of the sheet. Okay, does this make sense? This scale, does this make sense for an 8.5 by 11? Like, would you put a football field on an 8.5 by 11 sheet of paper at that scale? No, it's not going to fit, right? And keep in mind, like, this is just the object. We still have the title block and all that other stuff to consider, right? So does a 1 inch by 20 foot scale, or sorry, 1 inch by 10 foot scale, does that make sense? No. What about 1 inch equals 20 feet? Does that make sense? No, it doesn't, right? That doesn't make sense, okay? Now, what about 1 inch equals 30 feet? Okay, if I do the math, could I fit the football field on the sheet from a height perspective? Yeah, I could. The height of the object is, or the height on the sheet is 255 feet. So I could fit 255 feet of height on that sheet of paper, and the football field's only 160 feet tall. So I can do that, but it's too long, right? The football field is 360 feet long, and 330 feet is the maximum I could do. So what about a 1 inch equals 40 foot scale? Could I do that? Yes, I could. Okay. So I propose that if you're going to print a football field on an 8.5 by 11 sheet of paper, do it at a 1 inch equals 40 foot scale. Does that idea kind of make sense? The idea that you've got to select a scale that encompasses the object as much as possible. Okay. So far so good? Okay. All right. So let's do a quick scaling exercise. So this is going to be a two-part exercise. So the first thing that we're going to do is, as a class, we're going to do a quick practice with our scales. Okay. Okay, so I'm going to give everybody a minute or so on this, so the first thing I want to do is I want to make sure that we are comfortable with just the process of using the scale, okay? So I've given you 2 lines, and don't worry, on the homework I'm going to give you a few more, but I've given you 2 lines, okay? And what I want you to do is I want you to utilize the engineering scale to determine the length of each of these lines, okay? So I want everybody to take your time with this. We'll give everybody a minute or so. But to be clear, I'm not talking about the spaces on the first page. I'm talking about these lines on page 3 of the packet. So it should look like this. And if you're feeling charitable and you have a friend that forgot their scale, you can let them borrow it when you're done. So. What's that? Okay. By the way, all right. And by the way, if you didn't bring yours today, it's not the end of the world. I'm not collecting these, but Wednesday, bring them. Okay. Okay, we're going to give everybody a minute or so on this first one. We'll see if we have some agreement on the scale. Does everybody have at least the first one done? All right. Let me ask you a question. Does anybody have an answer for me for the first one? 91. Okay, hold on. All right. I have a lot of people saying 91. But on the 10 scale, let's keep in mind. So how about this? For the 10 scale, you could probably estimate one digit past that. Okay? So why don't we measure that again and see if 91, if you had to say 91 point something, 91 point what? Because on the 10 scale, you could probably get one more digit that's estimated. You can't do that on the second one, but on the first one, you probably can. Sure. All right, so 91 point what? All right, so I've got 91.3. How about you folks over here? How are we doing? Does that sound about right? Okay. All right. I got an answer from this side of the room on the first one. How about the second one? Okay, so the second one. Okay, so this is at a 1 inch equals 400 scale. Now you don't have a 400 scale, but you do have a 40 scale. So measure the line on the 40 scale, and then do what to that number? Multiply by 10, because going from the 40 scale to the 400 scale is a factor of 10. Somebody over on this side of the room, on problem 2, anybody got a number for me? 1420. Okay, do I have a second on that? Okay, we've got a second. What about my folks over here? How does 1420 sound?
Sounds good to me.
All right. Is there anybody that's getting totally different answers? Anybody get totally different answers? So we got 91.2 or 0.3 at about 1420. Everybody good with that? Everybody feel comfortable with that? Okay. So the idea is that if you know the scale, you can determine any distance on a drawing with the drawing with an engineering scale. Okay. Sound good? Okay. Now what I want to do is I want to look at our AutoCAD file. Okay, so let me open AutoCAD real quick. Okay, so if you haven't already done so, go ahead and open the AutoCAD file that's on Blackboard. What you should see is something like this. Now don't draw anything or edit anything just now, because I want to show you something that's maybe a little difficult to see. Okay, does everybody? First off, I think when you open this, obviously the first thing that pops out is the football field, right? But does anybody notice anything in the bottom left corner? Like, why don't you zoom in to this bottom left corner? What do you see? You see a page. Okay? So what I have here is I have a title block drawn to scale, and I need to do something with it. Okay? Now, so does everybody kind of get an idea of the structure of the file? Okay, now before we move on and actually start doing the exercise, I want to show you a few things, okay? So the first thing I want to show you is I want to show you the layers, okay? So everybody look up here, okay? So if you look up here, you'll see that I've created all the layers for the drawing. So I've got the field annotations, those are the letters and the marshal and the end zones on the football field. I have what I'm calling major yard lines and minor yard lines. So those are the tick marks on the field and the 5, 10 yard lines and so on and so forth. Then I've got a page border and a title block. Okay. Now the page border is red, but does anybody see the print icon next to the color red? Does everybody see that? This little print icon right here. Okay. What that basically means is that it will not print that border, okay, or that layer, okay. And so what I'm going to do is I'm going to use the window feature in the in the plotting options to plot that page. Okay, and I'm going to trace that border, but you're going to see where that comes in here in a little bit. Okay. Now, the first thing that we've got to do is we've got to scale the title block. Okay. But before we scale the title block, I have a command that I kind of want to show you, and the command is called the distance command, or DIST. For you Mac folks, there is no shortcut for this, but for Windows, it's in the measure toolbar under the home command, but you know me, or under the home tab, but you know me, I kind of just like to use the command, okay? So the command is DIST and press enter, okay? The distance command is sort of like the scale equivalent in AutoCAD. The distance command is used to just measure any distance in a drawing. Okay, unlike the dimension command where you're actually placing an annotation, distance is more just querying a distance, trying to figure something out. Okay, so like for example, if I use the distance command and I go, tell me what the distance from this endpoint to this endpoint is, you can see on the bottom it says that that is 11 units. Okay, and if I do distance again from here to here, it's 8.5. Okay, so what this is telling me is that this title block is drawn to scale. Okay, so if I were to print this, 1 unit here on this title block would correspond to 1 inch on the page. Does that make sense? Everybody with me so far? Okay. So you can do the same thing as well on the football field. So if I go up here to the football field and I say, let's measure this distance. If I go from end zone to end zone, I get 360. Okay, why 360? Because it's 360 feet. 100 yards plus 2 10-yard end zones. Okay. Now obviously, this title block does not make sense for this football field as it stands right now because it's at the wrong scale. Now, what scale did we agree was appropriate for a football field? What did we say? 1 to 40. 1 to 40. Okay, so here's what I'm going to do. I'm going to use the scale command, and I'm going to scale this entire set of objects up by a factor of 40. So what I'm going to do is I'm going to use the scale command, and it's going to ask me what objects to scale up, and I'm scaling up everything in the page border, everything in the title block. So all this, okay? It asks me for a base point. It doesn't really matter what base point you pick because we're going to move this anyways, but if you want, just pick the bottom left corner. It asks for a scale factor. We do a scale factor of 40. And yeah, it got a lot bigger. But now I could actually fit this this football field inside the title block. Does that make sense? Everybody with me so far? Okay, so now what we're going to do is a couple things. First off, let's move this so that it's in the middle. Okay, so if you want, we'll use the move command and move this. Now, if you want, you could figure out a way of getting it precisely in the middle, but for the purposes of this, I'm just going to kind of get it pretty close. I mean, there are ways that you could get this football field precisely in the middle of the page. Like you could draw some lines, but this is just me eyeballing it. And for the sake of our example, this is probably good enough. So all I did is I just moved the title block such that it fully surrounds the football field, okay? And that's just using the move command, okay? So let's just make sure we're all comfortable with that. Everybody good? Everybody good? How about everybody over here? Y'all doing good? So now what we can do is watch this. So now what we can do, we're going to do a couple things different. So we're going to go to File, Plot. Now we've done this before, but we're going to do a couple things different. Okay, so the first thing, we're going to do monochrome. We're going to DWG to PDF. We're going to use our full bleed paper, 11 by 8.5. Now, up until now, when it asks for what to plot, and we've been saying limits, we've been using the drawing limits that we specified. Now what I'm going to do is I'm going to use window. Okay? So I'm going to drop down here to window. And what happens is it pops back up to the drawing. It says, what window? What window am I doing? The page. And one of the things you'll notice is that if you did this correctly, because we're using full bleed, if you're fitting the paper, look what it's doing. 1 inch equals 40 units, right? Okay. We'll hit preview. And by golly gosh gee. Okay. Oh, I noticed I forgot something. I forgot to change the text block because I said 1 inch equals so many feet. So maybe what I'll do is I'll hit escape. Let's change this to 1 inch equals 40 feet. Now let's do all that again. Plot. Window. Monochrome. DWG to PDF. Full bleed 11 by 8.5. Center the plot. Preview. And boom. And when it's all said and done, you should get a drawing that looks exactly what you have on the last page. And you have a scale. Let's check and see if this last page makes sense. I mean, is this plotted to a correct scale? Did I do a good job on this last page? Well, why don't you tell me? How long's the football field? Using the scale. How long is it? And how did I do? I mean, did I do a good job? Is it to the right scale? How many tick marks is it? Or how many feet is it? 360 feet. 360 feet or 120 yards. Okay? Does that make sense? So that you are aware, here is what your homework's going to be like on Wednesday. What I'm going to do is I'm going to give you a three-dimensional rendering of a part. It is going to be rendered to a known scale, but I'm not going to give you all the dimensions. Okay? Instead, what I'm going to do is I'm going to say, some of the dimensions I'm giving you, some of them you're going to need to interpret with one of those. And then you are going to produce a drawing that shows front view, top view, and side view of this isometric part. Okay? That's going to be the goal of this week's assignment. Any questions? All right. So here's what I'm going to do. I'm going to let you all out a little bit early, but if anybody has any questions on homework 8, I'm going to stick around for a little while, see if anybody has any questions. I am going to pull the QR code up one more time for people that missed it. But that's all I have, everybody. I will see you all on Wednesday.